that it's, in our case, it's monotone increasing in the first variable, monotone decreasing in the second, right? But there's no reason per se. That's just a special case of us. So concavity, okay, and joint concavity, and that's it. It says assume there is a sequence x t star going from t equals 0 to t equal infinity. And the sequence satisfies the following properties. 1, x0 star equal x0. So it starts from the given initial condition. Property 2. The sequence satisfies the Euler equation at all t. The Euler equation is this. Okay? So if we replace the values of that sequence in here, it gives out 0 every t. We have to do this checking an infinite number of times, so we'll never finish, but it does so. There's 3. It satisfies the transversality condition, where it says the transversality condition is this. The limit of the discounted value of the marginal GDP consumption at t, multiplied by the marginal productivity of capital at t, okay? Oh, I have a doubt. Oh, Alzheimer. I'm not going to give up. For the first time in my life, I'm not going to start teaching with lecture notes. I never did. I cannot prove the transversality condition to check if I remember it right or wrong. Yes, I think it's wrong. There is xt here. I have to remember the indices. The reason I'm confused about the indices is because sometimes I use the index starting at 0, so now I use the index starting at 1, and that shifts. So I think that in this formulation it's like this. Okay? And it's the value of that. Okay, let's leave it like that. I will have to give in and think a moment during the break. Basically, because the concept is that the value of capital goes to, now, yeah. Now I remember. Okay. The value of capital, the discounted value of the stock of capital goes to 0, as I talked about. Okay, this is the present net. This is the present value of the price of capital at t. Okay. Yeah, that's what comes out when you, all right. So if the sequence satisfies these 3 conditions, then it's optimal. Okay, if the utility function is strictly concave, it's also unique. There's no other sequence, there's only one that does that. So the Mangasarian theorem is relevant because it gives you the certainty that by studying the Euler equation satisfying the initial condition, you pick the optimal sequence. Why? Because obviously in our model, x is bounded. So with x bounded, the transversality condition is automatically satisfied, right? This is a bounded number, this is therefore a bounded number, this goes to 0. So transversality condition, when you study problems that are bounded, is automatically satisfied. Never get confused though, because you get into the habit and then you study problems that are unbounded, in which the state variable goes to infinity, and then you make mistakes that many people have made in very famous published papers. They forget that they're actually looking at paths that do not satisfy the desired condition. So remember, the desired condition is always satisfied if it is bounded. If they're growing, it's gonna boil down to a combination of parameters that restrict what you admit. Right? For some parameters, basically think of what's going on. Right? This is going to infinity. This is going to 0, and this is also declining. It doesn't have to go to 0, but it's declining because consumption is growing. Bottom line, the product of these two have to decline fast enough to compensate for the growth of this. So the growth rate of capital cannot be higher than the degrowth or decrease rate of its price when expressed in present value terms. All right? So in particular, if you have a linear utility function, which gives you constant consumption, that gives you constant marginal utility consumption, then capital cannot grow faster than your discount factor. It has to grow slower. Right? That's the worst case. If utility is decreasing at the margin, then that contributes, so capital can actually grow faster than your discount rate, pure discount rate, as long as the marginal utility push down the thing. Okay? So, right. Okay, given that we studied the bounded problem, now that we stated Mangasarian theorem, we take away. So that's it. That's what we have to work with. We have to work with the Euler equation and try to make sense of it. How do you make sense of the Euler equation? Well, it's an ugly bastard. It's an ugly bastard because if you manipulate it a bit and you think that you have an infinite number of them, what is that you have? Well, you have the first, you can write it as an implicit function, right? The first is just g, say, of x0, x1, x2 equals 0. The second is the same g of x1, x2, x3 equals 0. And so on, g of xt, xt plus 1, xt plus 2 equals 0, and so on. Right? This value is given. Right? Now think of the case in which there is a finite horizon. Growth model were initially studied for finite horizon. Okay? Think of the case of a finite horizon. There is a finite horizon, typically there is a finite condition. If you take a look at the papers I sent you about turnpike theory, you will see that the way turnpike theory, the problem optimal accumulation was stated at the beginning by Samuelson and others, was always in finite time. I start from a certain x0, I have t periods. At the end of the t periods, I want to reach xt, capital T. In the meanwhile, I want to do things as well as possible. I either want to maximize consumption or maximize growth rate or whatever. All right? Well, if there was a final condition, you could put the final condition here. Right? Then you would have what? You would have t plus 1 times 0. Right? Equation with t minus 1 variable. No, you would have t minus 2, t minus 1, t. So you would have t minus 1, exactly. Equation, right? With t minus 1 variables to figure out. x1, x2, x3, up to xt minus 1. x0 and x capital T would be given. Complicated, not obvious that there is a solution, but we have tools to try to solve this thing by implicit function, blah, 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 rank condition to try to solve the vector, right? We would have the precondition. Well, this kind of intuition is what has guided people to try to solve it also for the infinite horizon. Right? Actually, the transversality condition that Mangasarian introduced in that form, it used to be expressed as transversality for finite time. It had to do, for example, to typical case of using this thing was, you know, shoot a body so that at a time t it reaches transversally, that it hits a certain target, typically bombing a city, you know, hit the castle of the king, something like that. That was the transversality condition, kill the guy, all right? And so the bomb at both the initial condition, the position, and the arrival, right? Obviously, the infinite horizon, that's not there, but you know, the good intuition of Mangasarian was, well, let's replace it with that particular form and it works, okay? When you start thinking of it like that, you start thinking of it as a dynamical system, right? This is in fact a dynamical system that always given two variable maps into other two in each period, all right? And then the study of the Euler equation becomes the study of, you take this, you kind of call variables in a funny way, and you end up studying a model that says xt and xt plus 1 are function of, sorry, xt plus 1 and xt plus 2 are function of xt plus 1, right? Well, obviously, xt plus 1 is a trivial function of this, it's just equal to xt plus 1, all right? And the second is that. So it's a 2x2 dynamical system in which you take 2 points and you map into 2 points. It's a bit funny because when I graph it, like in the square, this, x0 is given as an initial condition, but x1 is not. What I know is that x1 has to be included in this set. That's the production function, right? That's the set of feasible things, right? So if I start with this x0, all the admissible value of x1 are this. I'm going a bit fast. You guys have to study this. I cannot spend the whole class. I was hoping that the Euler equation would be taught somewhere. So I'm going to try to finish this, give briefly the dynamic programming, then we need to take a break because I'm also getting a bit tired. And then you have to go to the book and study chapter 3 and 4, and when you don't understand, bring it to me, otherwise, okay? So it's relatively easy to see you can go here from there, right? All you have to do is to call it the same, right? And this is just the implicit function. And you'll check the implicit function works if the utility function is twice differential. Okay? Strictly concave. As long as the utility function is strictly concave, you can actually write this function explicitly, x2 as a function of x0, x1, x3 as a function of x1, x2, x2 plus 2 equal functional, right? The function exists. And you have this. Now this is a dynamical system in a from here into here, right? You take a point from here, you plug it into phi, and it maps back somewhere, and then you map it back again, right? So that's what you want to study, okay? I am unable to draw 4-dimensional diagrams, so I have to do it like this, okay? What's the problem with this system? The problem is again the same, that I have one initial condition, but I need 2. And so at the beginning, all I know is that I start here, okay, that's the initial capital stock, and x1 has to be chosen to stay within this bound, because that's the feasibility bound. But God, that's a continuum of points. That's a lot of points. Okay? Well, what has helped people study the one-sector model? As you will see, this would not work in dimension 2, 3, 4, when there's more than one capital stock. But when there is one capital stock, so in the one-sector and two-sector model, something happens. And it is the following, so I'm going to give it very briefly. It is that when you go back to the Euler equation, and you ask, Jesus, does this thing have a steady state? Well, the answer is yes. And it's actually very easy to compute the steady state because it is that point at which this is true. Yeah? Why? Because the steady state is constant consumption, constant capital, so the marginal utilities of consumption cancel out, and the Euler equation boils down to what I just wrote. So it is that point x, or those points x, at which the marginal productivity is equal to the inverse of the discount factor. Because we have assumed that the production function is marginal, has decreasing marginal productivity of capital, f prime is a decreasing function. So as long as the marginal productivity is high enough, add 0, and low enough, that's the assumption, right? At a certain point, it will cross delta the minus 1. Obviously, in the footnote 6 case, it doesn't cross delta the minus 1. Right? As long as A is larger than delta the minus 1, it never crosses delta the minus 1, so there is never a steady state. But if there is enough decrease of return, this crosses delta the minus 1. Now, these are what people call the nada condition. Now people become too simplistic, nobody wants to make any effort anymore, so now the nada condition is all infinity, 0. It's a little less, it's just, it's just lim f prime of x for x going to 0, larger than delta the minus 1, and lim f prime of x less than delta the minus 1. Okay, that's enough. Right? It just crosses that stupid value. Okay? Good. So there's only one. Well, if there is only one, let's redraw the graph here. Actually, I'm not even going to draw the axis. I'm just going to put a point here, the 45-degree line. That's x star. That's the steady state. Okay? And here I have the boundary of the set. Okay? And now we take a break.